Hello, and thank you for joining me for this mind map session for Module 6 on the urinary system. Here we're going to primarily focus on the physiology of the kidney, so we'll begin with how the kidney filters and processes fluid, and then we'll get a little bit more into some of the specifics about how some of the hormones work to fine-tune some of that processing of the filtrate and reabsorbing or secreting things from the filtrate back into the blood, or secreting things from the blood into the filtrate so that it can be lost through the urine. So we'll begin with the processing of the fluid by the kidneys. Recall that approximately 180 to 200 liters of fluid is processed daily for the kidney, but only about 2 liters of fluid is actually lost as urine. So less than 1% of what the kidney is processing is actually lost as urine, which it would be pretty difficult to keep up with 200 liters of fluid loss per day. So it makes sense that the amount of urine that is produced and lost through the body, through the kidneys, is significantly less than the amount of total fluid that's actually processed. We'd have to drink pretty copious amounts of water to be able to keep up with 200 liters of fluid loss a day. So fortunately, the amount of fluid that's being processed by the kidney is not anywhere close to what's being lost as urine from the body. We had a couple of important processes that produce and then process the filtrate into urine. We had the glomerular filtration, which was the initial separation of some of the fluid from the blood in order to begin the processing. And then we had tubular absorption, in which a lot of the things that we need, like nutrients and electrolytes, and even water, are reclaimed by the kidney tubules in order to make sure that they are not lost in the urine. And then finally we had tubular secretion, which is the process in which the kidneys will secrete things into the urine, specifically waste products that need to be eliminated from the bloodstream before they build up to toxic levels. So let's look at filtration first at this fourth bullet point here. Where in the nephron does glomerular filtration occur? And we'll answer that question. It occurs at the glomerulus and the glomerular capsule. So the glomerulus, recall, is the structure of capillaries, the microscopic capillaries that are within in the glomerulus, or in the kind of surrounded by the glomerular capsule. And the capsule is the structure that captures the filtrate, that is the fluid that is filtered or removed from those capillaries. And the glomerular capsule then essentially kind of funnels the filtrate to the kidney tubules, where it will begin processing. So the capsule is also called the Bowman's capsule. And then we also have tubular absorption and secretion, of course, occurring, as their name implies, in the kidney tubules. So we have the proximal convoluted tubule, the nephron loop, which is also called the loop of Henle. We have the distal convoluted tubule, which is where the nephron ends. So the nephron ends at the distal convoluted tubule. But then recall that there's also another structure beyond the distal convoluted tubule. It's called the collecting duct. And the collecting duct is the site, a very important site where a couple of hormones can act in order to kind of fine-tune the filtrate. More specifically, kind of fine-tuning the amount of sodium or water in the filtrate, depending on which hormones are being secreted. And we'll see that in a little bit. So, next bullet point here: is glomerular filtration an active process or a passive process? So filtration is a passive process because it is mostly fueled by blood pressure, or it is entirely fueled, I should say, by blood pressure. That is the pressure of the fluid, the blood that's moving through those glomerular capillaries, is the force, the driving force for squeezing some of that fluid out of the glomerular capillaries and into the glomerular capsule to begin that processing. So that process is passive in that it doesn't require additional ATP input by the kidney in order to move that fluid from the glomerular capillaries into the glomerular capsule. And as I mentioned before, that main driving force or pressure is going to be blood pressure, which is entirely driven by the heart as well as some of the large arteries that we saw back in Module 2 and 3 when we were examining the cardiovascular system. Looking at the actual pressures that are exerted at the level of the glomerulus and glomerular capsule, we saw that there were 3 pressures that determine what's called net filtration pressure. And net filtration pressure is an important pressure because it determines how fast filtrate is going to be formed, or how quickly filtrate is going to be formed in the kidney. Because remember, it's the kidney's entire job to produce filtrate and then process that filtrate for nutrients and wastes. And so it's going to be really important for the kidney to be able to maintain a sort of baseline net filtration pressure so that it can continue to do its job as it is intended. So we've got 3 pressures that we looked at. One's called HPGC, which is collectively referred to as the hydrostatic pressure of the glomerular capillaries. This can also really just be looked at as a fancy term for the blood pressure in the glomerular capillaries, because the term hydrostatic pressure just means a fluid pressure on the walls of a vessel. And in this case, because the fluid that's flowing through the glomerular capillaries is blood, we can kind of deduce that or reduce that to blood pressure, right? So that is the main driving force for initially creating the filtrate. And then there were 2 pressures that opposed that: the osmotic pressure of the glomerular capillaries and the hydrostatic pressure of what's called the capsule space. Now, backing up there to the osmotic pressure of the glomerular capillaries, recall that in a healthy kidney, the glomerular capillaries do not allow proteins to move from the blood into the filtrate. So those proteins, like albumin, will stay in the glomerular capillaries and act as an osmotic puller of water or fluid from the capsule space back into the glomerular capillaries. So because proteins remain in the blood when the blood is filtered at the level of the glomerulus, that those proteins that remain in the blood act as an osmotic pull for water to resist the movement of water from the glomerular capillaries into the Bowman's capsule or into the glomerular capsule. So OPGC actually opposes the hydrostatic pressure of the glomerular capillaries, or the blood pressure of the glomerular capillaries. And then hydrostatic pressure of the capsule space is simply the fluid pressure of the filtrate that's already in the glomerular capsule, because those never completely drain. There's always a little bit of fluid in them. And just the fact that there is fluid in there, that fluid presence in the capsule is what resists the pressure, the blood pressure forcing more fluid out of the glomerular capillaries. So as long as the HPGC is greater than the sum of the OPGC and the HPCS, so that is, as long as the osmotic pressure of the glomerular capillaries and the hydrostatic pressure of the capsule space are not greater than the hydrostatic pressure of the glomerular capillaries, then filtrate will always be produced. So moving on to the bullet point at the bottom here, what are typical values in millimeters of mercury of the 3 pressures that determine net filtration pressure? Because recall that anytime we're dealing with pressure, whether it's fluid pressure like blood pressure, or air pressure like we saw in the, or atmospheric pressure like we saw in the respiratory system, those pressures are always expressed in units that are called millimeters of mercury. Right? And the hydrostatic pressure of the glomerular capillaries is about 55 millimeters of mercury, pushing fluid from the capillaries into the capsule space. And then the other 2, osmotic pressure of the glomerular capillaries and hydrostatic pressure of the capsule space, are both in the opposite direction of that. So OPGC is about 30 millimeters of mercury in a typical healthy kidney, and HPCS is about 15 millimeters of mercury. So if we subtract the OPGC and the HPCS from the hydrostatic pressure of the glomerular capillaries, as long as that value remains fairly high, or somewhere in the 8 to 10 millimeters of mercury realm, so that means that hydrostatic pressure of the glomerular capillaries should always be a little bit higher or a little bit greater than the sum of the osmotic pressure of the glomerular capillaries and the hydrostatic pressure of the capsule space. So that fluid is, and what that number tells us is that as long as that number is a little bit higher than those 2 numbers combined, that means that filtrate will always be created at a fairly normal rate inside of the kidney. Moving down here. Define GFR, which is called glomerular filtration rate, and state in milliliters per minute a typical value for GFR. So GFR is simply the volume of filtrate that's formed by both kidneys in a single minute. So because it's a rate, that's per unit time, and because we're measuring a fluid in milliliters, that means that our units for GFR are milliliters per minute. Typical values in a healthy kidney are about 125 milliliters a minute for an average healthy adult. Now notice, because that's filtrate formation and not urine formation, we're not producing 125 milliliters of urine per minute, we're producing 125 milliliters of filtrate per minute. But remember, it's only about 1% of that, or slightly less than 1% of that, that's actually becoming urine each minute. So I believe the number for urine production each minute is about 0.9 milliliters or something like that. So it's 9/10 of a milliliter per minute of urine production. So very significantly less than the overall filtrate production. So next we'll start to get into some of the mechanisms for how GFR is regulated in the kidney. We'll look at first what are called the intrinsic controls, and then we'll look at the extrinsic controls that regulate both GFR as well as systemic blood pressure. So first we'll look at what are called the intrinsic controls, which are collectively also called renal autoregulation. And renal autoregulation, or the intrinsic controls, are the controls that the kidney uses to maintain GFR regardless of what else is occurring in the body. We had two mechanisms in renal autoregulation. We had the myogenic mechanism, and we had tubuloglomerular feedback. So we'll look at the myogenic mechanism real briefly, and then we'll move on to tubuloglomerular feedback. Myogenic mechanism uses muscle contraction in the afferent arteriole of the glomerulus in order to control how much blood is flowing through those glomerular capillaries. So when you see the term myogenic, I want you to think myo as in muscle, right? So there are smooth muscles that are in the walls of the afferent arterioles that are feeding each of those glomerular capillary beds. And it's really, really important, just like with blood pressure in the rest of the body, that the diameter of that blood vessel, that afferent arteriole, it's really, really important for the diameter of that blood vessel to control how much blood is flowing through those capillaries at any one given moment. So when blood pressure is high, constriction of that afferent arteriole will protect the glomerulus from damage, because what we see in the glomerulus is that those capillaries actually we saw that the typical pressure in them is about 55 millimeters of mercury, which is more than 2 times higher than a typical capillary bed. Typical capillary beds only have about 20 millimeters of mercury of pressure in them. So they're still capillaries, they're still very delicate and very susceptible to damage, especially when blood pressure gets really, really high. So it's important to have this myogenic mechanism in place in order to make sure that that blood pressure in those glomerular capillaries doesn't get so high that those capillaries rupture, right? So when we see that blood pressure starts to rise, that is systemic blood pressure starts to rise due to hypertension or other factors, constriction of that afferent arteriole is going to protect the glomerulus from damage, because it's going to slow blood flow to those capillaries. So we saw that dilation or constriction of blood vessels controls blood flow, which was determined by Poiseuille's law that we saw back in module 3, for blood pressure. And Poiseuille's law was really heavily dependent on the diameter of those blood vessels, right, to control things like resistance to blood flow. So we saw that diameter of blood vessels is really, really important for changing resistance and changing blood flow to blood vessels.